Yeah, I'm Matthew. I'm a Earth observation data scientist at Geoscience Australia. I'm also a computational radio astronomer, so that's fun. I'm presenting today from Ngunnawal in Ngambri country. I'd like to pay my respects to the traditional custodians. Right, I'm going to present today a problem in both fields that I work in that doesn't really have a good answer. So don't expect too many answers. The product I work on is called Digital Earth Australia Waterbodies. It's about 300,000 polygons that we've derived from satellite data representing water bodies throughout the Australian continent, as well as time series over the past 30 odd years that we've extracted from Landsat data for each of these. This is a super cool data set. I like it very much. We find water body polygons automatically from the satellite data. We run a classifier, a machine learning classifier on every single pixel of our 30-year archive to find where all the wet stuff is, tally it up and find stuff that's wet more than 5% of the time and call that pixel part of a water body, aggregate them all together, and that's what we call a water body polygon. Picture on the left shows you a frequency summary of how wet things are, and on the right was a set of polygons. The polygons, though, are very, very dependent on the projection that you use to represent your raster data. Because, of course, if you have a different coordinate grid, you'll get a different polygon out. And on the left here, I've got a picture of two different coordinate grids, which have provided two different polygons of the same water body, one in blue, one in orange. You also get this problem if you come in from different satellites. So on the right, I've got a picture of a Sentinel-2 derived polygon that has 10-meter resolution, overlaying the same water body derived from some Landsat data, which has 25-meter resolution. This can be a little bit problematic for us. We need to match up polygons that come from different reference systems because they are different, and we base the names of our polygons by their centroid, which changes if you change the edges of your polygon. We care about these names, stakeholders care about these names. It's important that we be able to identify when two polygons are the same in different data sets. There is, of course, an obvious algorithm to go about doing this. You take all the polygons in one data set, you take all the polygons in another data set, and you check where they intersect. Wherever they intersect, you say these are the same polygon. Again, these are some real examples. On the left, we have some polygons from one reference system, and on the right, we have it from another. They're both from Landsat data. There are problems with this. Here is one particular case. You have a polygon that in one data set is just one polygon, but in the other data set, it becomes two polygons. And so it's not a simple one-to-one matching task. You can also have the inverse problem where you have multiple polygons, in this case two, that become one polygon in the result data set. So it's actually a many-to-many matching problem, which is already pretty hard to deal with. But there are even trickier problem cases like this one, where we have two unrelated polygons that when you go ahead and you intersect the two data sets, they actually overlap with each other. And so you can see that if we were just following an intersection algorithm to merge these data sets, the top and bottom polygon would actually be considered the same. And all of these polygons in this picture would be the same water body, which they're clearly not. Let's talk about radio astronomy. We use telescope arrays in radio astronomy to conduct interferometric measurements of the radio sky. And we get to see really cool objects like this radio galaxy on the right that was taken with a very large array. We have very creative names for our instruments in astronomy. That's the very large array on the left. And I'm going to tell you about a related problem in that. I like radio galaxies. Here is a collection of radio galaxies. Unlike a lot of space objects, they're pretty big, they're extended on the sky, they're diffuse, they have interesting structure. And we have a lot of things we would like to be able to do with them. On a large scale, we need to break down our images into small components that we can actually analyze to facilitate automatic analysis. We have hundreds of thousands of these objects. And so we'll either fit Gaussians to it, like on the left, or we'll do something very similar to water bodies, threshold areas, and call them a component. And in this way, we break down a survey of a single raster image into lots of small polygons. We then need to match those polygons if we have multiple surveys so that we can do multi-frequency analysis or other kinds of science. It's also really good for validation if you have the same telescope, two different surveys, but one of the surveys was conducted a little differently and you want to check that everything matches. Still need to be able to match your components across surveys for doing that. Resolution and frequency have really unusual effects in radio imagery because different physics emits different frequency radio, and also due to the interferometric nature of radio observations, resolution can actually change what physics you see. These are the same object in these pictures. Same telescope, same frequency, the only difference is the resolution, but you can see on the right, there's clearly one big, long, extended object. So we have another matching problem. We need to be able to take things in one radio survey and match them to things in another radio survey, even though they might look totally different in these two different surveys. This is, again, the same object, and it looks completely different in these two different surveys. Sometimes it's trivial, sometimes it's not, because of the way they look different. This is, of course, the exact same problem as we face in DEA Waterbodies. You have a collection of polygons or shapes or some object, which I put down the left axis here. You have another collection across the right, and you want to match them up. You make a really big matrix, which is extremely sparse. Almost everything says, no, this is not a match. And then you have a handful of things that do, in fact, match. You could also, if you want to represent this as a bipartite graph, you have one set of data on the left there, one set of data on the right there, and you want to draw lines between the two. You can represent priors and easy cases as well by drawing in the ones that you're really sure about or the ones that don't really have any alternatives. So it's a graph completion problem in machine learning parlance. These two problems have a lot in common with each other. They have similar quantities. There's 300,000 water bodies, 900,000 radio components. There's an extremely sparse matching matrix. They have the same problem cases, the same failure modes, and the same objects can be very different looking in different data sets, which until I started doing Earth observation, I thought was unique to radio astronomy. The other really interesting thing that they share is that there's spatial information. There's shapes in both, and they actually occupy a location. This makes them unique out of all kinds of graph matching problems. There is actually some spatial prior you can put. That's all from me. Thanks.